Hello, Year 11. Welcome to our second video for polynomials. Here we go. What we're going to do today is graphing polynomials. This typically is not as hard as it sounds. So, 3 steps here we've got jotted down. Find the y-intercept. Okay. When the polynomial is in expanded form, right? If it's not been factorized, then the y-intercept is the constant term. Okay, the constant term is the y-intercept because if you let x equal 0, all of the other terms become 0 and only the constant is left, so that's our y-intercept. Identify the shape. Now I need to explain this a little bit. We know that a linear equation is a straight line. And if it has a positive gradient, it goes from typically the third quadrant to the first quadrant. It mostly exists in the first and third quadrants, right? It goes up from bottom left to top right. A quadratic is like a U shape, and it can be concave down if it's positive or concave up if it's a negative leading term. A cubic is going to look like this, right? If it's positive, right? Up, down, up. Or if it has a negative leading term, it's going to look like this. There are some slight exceptions to this, but for the time being, that's positive and negative. And you sort of see that if I ignore the bit in the middle, if I just look at the ends, then that follows the same sort of pattern for linear functions as well. Now, a fourth power is going to potentially do this, like a W, or like this, or an M. If it's a negative, try to get those curves smoother than I've written there. Okay, that's a fourth power, positive and negative, much like the quadratic at the outside. It's only on the inside we get more sort of wobbles. The power of that, the degree of that polynomial is going to be the maximum number of possible x-intercepts. Okay, so if I have a linear equation, right, that can only have one x-intercept, and in fact it always will. A quadratic can potentially cross twice, it can potentially cross once, oops, or it can potentially have no x-intercepts. Okay, but it has a maximum of 2 x-intercepts. A cubic has a maximum of 3 x-intercepts, a quartic of 4, and so on. Now, we find those using the factorized form of the polynomial, and for the time being, we can expect to have the factorized form. And using the null factor theorem, then we find what the zeros of that equation are. So let's have a look here. First of all, I have a polynomial here, y equals 2, that's f(x plus 2, x minus 1, x plus 3. Now, first of all, it is, right, the order, or the degree of this polynomial, x by x by x, will be a third order. It is a cubic, and that's a positive, 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 so it's going to be positive. So my general shape is going to look like this. If I can give you some advice, draw your curve first, draw the axes in later to match the intercepts. Now, my y-intercept is going to be the constant. So when I expand this out, right, the constant is going to come through when I do 2 by 2 is 4, by negative 1 is negative 4, times 3 is negative 12. Okay, negative 4 times 3. So my y-intercept is going to be negative 12. Now my intercepts are going to occur at, right, if y equals 0, then either 2 can't be 0, so x plus 2 could be 0, gives me an intercept at negative 2. Negative 3 gives me a 0 and 1. So what happens here is I've got 3 intercepts. They're occurring at negative 3, negative 2, and 1, which means that my y-axis goes in here. There's my x-axis. There's my y-axis. That must be negative 12. Not to scale, but that's okay. I've got a fairly smooth curve, as well as I can do it on this sort of screen here. I've got a fairly smooth curve. I have my intercepts at negative 3, negative 2, and 1. They're my x-intercepts. And my y-intercept is at negative 12, because that's the constant if I expand that out. Now moving on to example B here, this looks a little different. Why is that different? Because it has a squared. Now, where I have a square, if you can remember back to graphing quadratics at some stage in the past, we haven't done it yet this year, But where I have what we call a root of multiplicity, or a 0 of multiplicity 2, there are 2 roots here at the same spot. What happens there is I get like a tangent that it touches but doesn't cross over. So I have 2 roots, right? 2 identical roots at x equals 1. So we've got that there. 5 plus x, that's just being sneaky. That's the same. We could write that as x plus 5. Don't sweat that one. So I have the degree of this polynomial is, I've got 2 x's here, x squared. So 2, 3, 4. So this is a polynomial of degree 4, and the coefficient is going to be negative because of the negative x here. So it's 4th order with a negative, and that means that it's going to look roughly like this. Yeah, roughly like that. Now my zeros are going to occur at 1, right? I've got a double root at 1, at negative 5, and at 2. 1, negative 5, and 2. So this is going to be my double root here. So it's going to be my negative 5. So it's going to look like this, roughly like this, okay? Negative 5, 1, and 2 with the axis. Something like that. Now, it's important that these are drawn fairly neatly. Now that I've got a rough idea of how it looks, right, I'm going to redraw that again. Draw the curve first. Okay, make sure it's not vertical at any stage, no sharp curves. Now, my x-axis needs to come in at a tangent to that here. Probably a bit better if you've got a ruler to line that one up. And we said that was a double one at 1, so my y-axis goes in here. Label the x, oops, x here and y here. I shot at the top of my head there. This was at negative 5. This here is at 1. This here is at 2. Again, not to scale, that's not that important. Okay, I've got the curve here. Nothing's too vertical, nothing's too straight. This line here should be more neatly curved. So that's just how it went. I also need to find my y-intercept, and that's my constant. So negative 1 times negative 1 is 1, times 5 is 5, times 2 is 10. So that's up there at 10. Okay, there we go. That is graphing polynomials. There's a bit of work to be done in that. Practice them. These doubles. Now, if I have multiplicity of 3 here, a 0 of multiplicity 3, then what happens is I get something like this. Okay, where it goes across and back up again. I get sort of 3 roots in the same spot. It doesn't go up, down, up again. It goes up, across, up. So that's multiplicity 3, and frankly a 5, a 7, a 9, and so on. If I've got a power of an odd power here, then I get something a bit like that going on. So 3, 5, 7, and so on. It'll look a bit like this. Just really, you can check it out on Desmos. It sort of becomes a bit squarer and a bit flatter. And where I have an even number here, then I get this. Oops, this going on. Or perhaps I get, you know, it sort of goes, it becomes more beaker-like. Still not quite flat, and no sharp corners or anything, but it becomes that for positives. Both of those positives, and the negatives go the opposite direction. Anyhow, we'll work through more of those in class. If you've got any questions about what's happened here so far or anything else that pops up, make sure you jot them down so you don't forget, and ask me in class. See you there, guys.